I somehow managed to become a little bit sick, so I already apologize. But yeah, let's see. So yeah, I will talk today about joint work with Daniel Kane and Shahar Lovet from San Diego. And I kind of changed the title. The paper has a different title, but I think this paper is about how powerful comparisons are. So the first lower bound, I guess, we see in undergrad is for comparison-based sorting, and we also have an algorithm, MERGE sort, that achieves this lower bound. It's in a non-uniform model, and in this work we'll see how a geometric point of view, together with some probabilistic techniques, can show that in fact just with comparisons you can, in a non-uniform way, solve many basic combinatorial problems that actually, yeah, so this is the good news. Like, the algorithm has very little resources of just comparisons, and it can do many non-trivial tasks. The bad news is that we kind of give a barrier. So there was a hope that, for some of these problems here, K-sum, for instance, there was a hope that there will be a non-uniform lower bound in some model that we will explain, that will explain why this problem is hard. But what we show is that even in a much more restricted non-uniform model just uses comparisons, it's already possible to solve this question very fast. And this is kind of a barrier, so we should find another explanation why these things are hard. Okay, so let me begin. Yeah, so this is the outline of the talk. And let me begin with the problem definition. Okay. Yeah, so I abstracted out all the problems we'll be discussing. So the setting is like that. We have some finite set of Euclidean space of dimension n. And we have a class of functions. So it's some class of functions. Real. So it's from Rn to R. Okay. So for example, X will typically be a subset of the Boolean cube in our context, or more generally, a subset of z to the n integers with with small coefficients, with bounded norm. And F will typically be a class of polynomials. We will focus mostly when it's linear, when F is linear functions, but I will also mention the other cases. Now the point is that every F in F partitions X to three sets, to three parts. All X such that F of X is less than 0. All X such that F of X equals 0. And all X such that F of X is greater than 0. Okay, so we have a partition to three parts, and the goal is to determine this partition using what? So the goal, so this is the high level problem, goal, find, so let's call this partition P of F, partition of F. Find P of F using query access to F with minimal number of queries.
Say find P of f using answering queries about P of f.
No, find P of f is really determine P of f.
Like learn it.
The algorithm should be able to learn it. The algorithm should be able.
So what does the algorithm out? A function that computes P of f?
The algorithm outputs P of f. You can think of it as the algorithm gathers enough information to output P of f. Okay? Okay, now what are the allowed queries we will consider? Okay, so I need to specify what are the allowed queries, and we will consider several types of queries. So, types of queries. So we have label queries. The terminology is taken from active learning. From label queries are just what is the sign of f of x, where x is in x. Okay, so sign of f of x can be either positive, 0, or negative. It's a 3. We have comparison queries. Which is sign of f of x minus f of y, where x, y are in x. So this is just asking whether f of x is greater than or equal to f of y. And we have membership queries, which is sign of f of x, where x is now in Rn, an arbitrary point. So the difference between a membership query and a label query is that in a label query we're only allowed to use points in the given set, while in a membership query you can ask outside. Okay? And also notice that when capital F is a class of linear functions, then every comparison query is a membership query on x minus y, right? Because f of x minus f of y is just f of x minus y. Okay, so can you tell me like what is the geometric picture when f is, let's say, polynomial of degree 1, an affine function? So we have this function f. The kernel of f is some hyperplane. Then we have the positive side and the negative side. Then we have the points in x. And the label query is just picking a point and asking what is it labeled. Is it on the positive side or the negative side? A membership query is picking any point here, for instance, and asking what is it labeled. And the comparison query basically picks 2 points and compares their distance from the hyperplane. Right? So that's the geometric semantic. Okay, great. So this is the abstract problem. Now we will see several examples to see that we can express many well-studied problems in this setting. But are there any questions about the setting? Yeah?
How are you going to give the function f, or the class of, I mean, linear, just say it's linear, I mean, is there any sort of more...
Think of it as an information theoretical problem. There is no, I don't worry now about...
so the class is known to whoever is supposed to discover.
Your algorithm may depend on the class f and on the set x. Yeah, by the way, we will mostly consider algorithms that only use label and comparison queries. but there are some very nice open questions about membership queries, long-standing open questions that I want to present, and I also, if I have time, I want to make an analog with communication complexity that maybe it's not a good analog, but it's okay. So let's see some examples, and I will also state the main results. Okay. So, yeah. So the first example is what we call K-sum. So in K-sum, the problem of K-sum, we are given an array of n numbers, n real numbers. And the goal is to determine whether there is a subarray of size at most k whose sum is 0. Okay? So when k equals n, it is subset sum. It's one of the famous NP-complete problems. But also the case of k, well, when k equals 2 is trivial, right? We just need to traverse the array and see if there are two numbers that are with opposite signs. And already when k equals 3, it's an important problem that was studied in this fine-grained context, so especially for geometric problems. Okay, so I claim that K-sum can be embedded in this setting. So let's see how we do it.
So I think I missed something over there. Is X, so the algorithm knows X, and it's like, how big is it?
It will typically be like a subset of 0, 1 to the n.
No, but I mean, how is it given to, or it's just, is it like exponentially big, or?
You don't know, you know it.
Let's see this example and then.
The only input is our query. It's like a decision tree.
Yeah.
The only access to data, to F, you want to find F or P of F. And the only access you have is via this query.
But
X
I
and
want to know if there's such a linear over, what kinds of access.
Yes, as a function of x and f, sometimes we will be able to do very efficient things, and sometimes not. But well, let's see this example, and then if it's still not clear. Okay, so now I want to express K-sum as an instance of this abstract problem. So in K-sum, x is defined to be the set of all, let's call it x, small x, such that sum xi is at most k. And f is all linear, let's write it differently. F is all function of the form x goes to w dot x, where w is in Rn. Yeah, so this is just, so that's the inner product. I don't want to do this left angle and right angle all the time, so just, so f is the class of all linear functions, and x is all Boolean vectors of sparsity at most k. Yeah, so now I claim that an input w, so we're given an input w for k-sum. We need to determine whether there are k entries whose sum is 0, at most k entries. So think of w as a linear function, as the normal of a linear function. I claim that there is a subset of size at most k whose sum is 0, if and only if there is an x in x whose inner product with w is 0, right? Because what is the inner product? It's just summing the corresponding entries. Okay, so now let me state the first result. Okay. Yeah, so what are label queries in this context? What are label queries?
Which are positive, which are negative. You ask whether.
Yeah, you take a particular subarray of size at most k, and you ask, is the sum positive, negative, or 0? What are comparison queries? You take two subarrays, and you compare their sum. And membership query is what they call linear decision trees. You take an arbitrary linear combination of and you ask what is it, what is the sign. And and here also, this okay. So let me state one result. So all the results I will show now are all corollaries of one theorem, which we'll almost prove today, if I hope so. Yeah. So theorem. For every n, there exists a label comparison based algorithm that decides k-sum on inputs of size n using order of k times n times log square n queries. Okay, so notice that for every n, the algorithm depends on m. It's a non-uniform algorithm. And okay, now let me tell you a little bit about the history that I actually only recently learned. So, yeah, so
queries to what? So those are what kind of queries?
Comparison label-based algorithm means only comparison and label queries.
But the queries of size n, or this is
okay, no, label comparison queries. This is well defined, right? X is all vectors of sparsity at most k. So a label query is you take a particular subset of size at most k.
If I wanted query complexity in terms of the array, it would be k square and log square n. If I charged you for every query to an individual entry, it would be k square.
It's another factor of k. And every query looks at k and so 2k.
I'm not sure we're on the same page. What do you mean? So the query is just, you pick a particular subset or two subsets of size at most k, and you pay $1 for that. For every query, you pay $1.
If you're paying for each entry in the, database.
Why would you consider such?
Natural model.
Ah, okay. Okay, so I didn't understand the, okay. Yes.
What if you charge per entry, not per?
Yes. So the sparsity of the queries is at most 2k, right? Because comparison query can be sparsity is at most 2k of each query.
But the running time of this is more than the k.
It's a non-uniform algorithm. It's a decision tree. If you, it's a non-uniform algorithm. So for every n, I give you a decision tree, which uses this kind of queries, and the depth of this decision tree is what's written there.
But if you wanted to algorithmize it, would you?
Probably not, right? Because if you
Contradicts.
so even if you plug in k equals n, you get subset sum, and we don't think there is an algorithm with n square log square n for subset sum.
No, but for small trees.
Yeah, so that's a good question. I mean,
For small case, it's sort of contradicts.
yes, but
K equals 3.
yeah. Let me maybe discuss a little bit the history. So already the case of k equals 3 is an important problem. It's a complete problem in some sense for many geometric problems, and
Also for triangle finding a graph.
right for if there is a zero-sum triangle, you're given a graph and you have weights on the edges, and you want to determine whether there is a triangle whose sum is 0. But okay, so a little bit about. So there was a lot of research about this problem. So there is a folklore algorithm that solves it in roughly n to the k over 2. Yeah, n to the k over 2. There is an upper bound. This is kind of folklore. And this uses only k sparse queries of sparsity k. Notice that we use sparsity 2k. Okay, then Ericsson showed that there is also a lower bound, matching lower bound if you only use k sparse queries, any linear queries that are k sparse. Then Eilon and Chazelle showed that if you use any queries of sparsity less than 2k, then there is still a lower bound of n to the 1 plus some omega of 1, as long as the sparsity is less than 2k. So this matches our upper bound. Once you allow sparsity 2k, you can get it all the way down to quasi-linear. And then, yeah, in 2014, Gronlund and Petty improved this upper bound to a randomized decision tree that does something like O to the n over. So they just, then there's some log n here. And that was kind of considered a breakthrough. And then later, Sharir and Gold removed this square root log n.
Why is that better than?
There's no ceiling.
There's no ceiling, yeah.
So
Yeah, yeah. It's, and then, okay, and then when there are no restriction on the queries at all, so you can use unrestricted linear functions, then we can do it in the best result was order of kn log n, all of this squared. And this is due to Ezra and Sharir, and this improves on many previous work by Meyer of der Heide from 84, Meiser 93, yeah, Cardinal, Iacono, and Ohms 15.
All of these are confused about when it's non-uniform.
It's all of these are in the non-uniform model, okay? This result by Gronlund and Petty, they also used the non-uniform algorithm to shave a log factor from the n squared algorithm for 3-sum. And I heard that Sharir and Kaplan did the same thing with our.
I don't understand why did it take Sharir and whoever to get this upper bound where it follows directly from Meyer of the Heide, some polynomial.
Yeah.
Yeah, so you didn't state it. I mean, it's the polynomial upper bound Meyer of the Heide is 30 years old.
Yeah.
It's better than the things you mentioned.
No, but these are sparsity. These are low sparsity. Sparsity.
These are all low sparsity.
Yeah. With sparsity 2k minus 2 or something like that. Yeah. So these things are for low sparsity, and the.
So in this case, in this example, you also have it for membership queries. If you
No, so our algorithm only uses comparison and label queries.
yeah, but because it's linear, if you do comparison, it's the same as a membership query for -1 plus 1.
Yeah, very particular kind of membership query. Yeah.
I see, but so that's kind of the structure is kind of specific. So the linearity makes it that all your queries are in a sense labeling queries and
Membership.
roughly proper.
Membership queries. All the queries are membership queries, and of a special kind. Yeah. Okay, so that's the first example. I want to do now another one. Okay. So the second example is sorting.
Are any of those algorithms, the n to the t over 2?
Probably yes. Yeah.
So
No, I mean,
is that the reason for the handicap somehow that
there is.
we're trying to solve?
Let's consider the case of k equals 3. Okay. Plug in k equals 3, you get n square root n algorithm for 3-sum, and this is conjectured not, as far as I understand, the conjecture is that
But that one is
it won't happen.
upper
Yeah, the upper bound is
Yeah,
algorithmic.
and,
The conjecture is that the n to the k over 2 ceiling is the best for case. Right?
Okay, yeah, I know only for 3 at least. For 3, yeah, the conjecture is for
So
k.
basically for 4 there is an n square algorithm also. That's what is the
Yes. The algorithm for this algorithm is pretty simple.
you just take k
Like
over
meet in
2
the middle
subsets,
attack?
and you evaluate all k over 2 subsets.
And you sort them.
You solve them and you look for.
And then you traverse the array in a smart
it's
way.
like
To
meet in the middle. That's
Yes,
how it should.
Okay, so let's move to sorting. Okay. Okay, so in sorting, I'll give you what. So x is ei minus ej I j in n. Yeah, so it's the difference of pairs of unit vectors. And f is again same thing. X goes to w dot x. X is in Rn. Okay, now what I claim is that given an input array W, the order type of W, the order type, you know, of W is completely determined by P of W, by the partition induced by W. So for example, Wi, okay, so the order type, it's the permutation, so what is the order type? It's the permutation.
The permutation you get after sorting.
Yeah. It's a permutation you need to apply to W to bring it to sort it, in order to sort it. So there are n factorial order types. So yeah, so Wi is less than Wj if and only if the function W evaluated on ei minus ej is positive. Wi is equal to Wj. There are more than n factorial types, because there could be equalities. Wi is equal to Wj if the function evaluated ei minus ej is 0. Okay? Sorry?
What you just said.
Yeah, so I'm saying that if we know the values of these functions, whether they're positive, negative, or 0, on all of these points, we can sort W. We learn the because, yeah, there's. Okay, does this make sense? So, okay, now is the confusing part. What is a label query? What is a label query in this context? A label query is a comparison query. Yeah, so if you have good notation, I'll be happy. Is a comparison query in the context of sorting. Let's call it sorting comparison. Right? I just evaluate, I ask whether W of ei is greater than W of ej. That's it, right?
Would be nice if you could find X and F so that label is comparison, comparison is membership, and membership.
I'll think about it. Okay, now the next confusing thing. What is a comparison query? So this is not, I don't know if it's something standard, but can you just explain me?
The difference between comparison.
Right. So what is, so I let's say I know that W of I is greater than W of j, and I know that W of k is greater than W of l. So I check, is W of I greater than W of j more than W of k greater than W of l? Right? So it's a difference comparison queries.
If the sum is bigger than another sum.
Yeah, but why would you do something like this? Difference. No, I think this is kind of natural, right? Different. You ask, is this element greater than that element, more than that element? I mean, it's I don't know. It's intuitive. Difference comparison queries. Okay. So let me now state. Yeah, so we know that there is actually a uniform algorithm, merge sort, that basically determines P of f using n log n label queries or sorting comparison queries. And what we show is the following. The theorem.
Still, there should be still an analog and low bound because you are just getting binary.
Yeah, so the n log n log, yeah, so this is tight. Merge sort is tight, information theoretically. There is but wait, 1 second. So let A equals B equals N. So these are just A, B are subsets of R, input subsets of R.
So this is a Friedman question.
Yes, yes. So we can sort A plus B. Yeah? A plus B denotes all possible ways to sum an element from A and an element from B. So A plus B can have at most n squared elements, n choose 2, but it can have also much less if A is, let's say, all the numbers between 1 and n. So we can sort A plus B using, and when I say can sort, I mean in this non-uniform sense, using order of n log square n, comparison and difference comparison queries.
This does not violate the information theoretic bound because the number of possible orderings there is not so.
No, so
Even though
it doesn't violate, yeah.
Yeah, I'm just
Yeah,
saying,
yeah.
I mean, you didn't say anything about it. In fact, you should have stated that n log n is a law. Information theoretic law bound still applies here because you have just a binary query. So this holds for all your models. The number of partitions, log of this is always a law.
Yes, yes, yes. So let me repeat what Avi just said. So in general, let's go back to the abstract question, right? What kind of queries do we have here? Our queries have, there are three types of answers. So we know that the number of leaves in any decision tree, right? So any algorithm here is basically a decision tree. The number of leaves in every decision tree must be at least the number of feasible partitions, right? And the number of partitions is the size of x, typically, is the size of x to the dimension. And you take the log of it, you get the log bound for the depth. So
this log square is tight for that?
I don't know. No, I don't know. I don't know.
Maybe n log n. Can be n log
I
n.
guess I would guess that n log n is the right answer.
The law bound is n log n.
You think that the
Yes.
number of orders of the sum set is determined by the order of the basic set?
Yeah, you can calculate it from it. It's not. It's
You don't have to take
Yeah. So let's
down-
let's do this. Let's do this. So let's say I have A and B. I want to model it now in this setting. So so I have A and B. So now X will be a subset of R to the A plus B. So it's like R to N. And again, the F will be linear functions. Now, given an array W, a linear function W, what do I want to know? I want to know that, so let's imagine that A, these are A, the first n elements, and the second n elements are B. So I want to know for every pair of vectors here, so I will have 1, 1, minus 1, minus 1, something like that, right? Right, so I want to know whether AI plus BJ is greater than or equal to AK plus BL. So these are, right, once I know the partition induced by W on all vectors of this kind that have exactly 1, 1, and 1 minus 1 in the first half, and exactly 1, 1, and 1 minus 1 in the second half, then I have enough information to determine the order type. I know the order type of W. Okay, does it make sense?
Is that your question?
No?
To show n log n lower bound for sorting, you say that the number of permutation is n factorial, right? So you have to all the
No, but
permutations have to appear. Right,
But
so-
yeah, but here that's exactly my point. So not all the permutations.
How many? He's asking.
Yeah, so how many permutations? How many vectors like this do we have?
For a subset, how many different
I'm answering, how many points do we have like that? Roughly n to the 4, right? Right? And how many, and and how many labelings of such points, how many partitions. We have a set now of n to the 4 points in Rn, and I ask how many partitions by half spaces can you find there. So it will be n to the 4, all of that to the n. So it's the size of the set to the dimension, which is much less than n cubed squared, n squared factorial. So it's something like n,
It's not n factorial.
n to the 4n.
N to the 4.
It's always the number of partitions. So this is the only. So there's one basic statement that if you have n points in Rd, the number of partitions on these points by hyperplanes is n to the d. And I reduced asking how many orderings, how many order types you have to this kind of problem. So I gave a set of n to the 4 points in Rd in Rn.
So the log one
Is n log n.
just by constant. It's like 4 log n, 4n log n instead of 2n log n.
Yes. Okay, I hope I didn't. This is not so important, actually. I mean,
What was
so,
that?
but
Can you tell us what was now?
no, so not,
Squared was
yeah, n squared. There's
Friedman sort of, I mean, the idea in the 70s, he posted this problem to show that, even though there are n squared elements, and the obvious way to do it is n squared log n, n squared log n.
Yeah, that's great.
You can have a non-uniform algorithm which just uses less than that. So
Just
beating
didn't know.
this information, it doesn't beat the information. Anyway, it was something like n squared.
n squared. Yes.
I guess he's just using, I guess there's one difference, he's just using.
He's using the label queries. Yeah,
That's
yeah,
right,
yeah.
just using label queries,
Yes.
and I don't think you can beat it.
Right. He also gives a lower bound that if you only use label queries, you cannot do better than n squared. So the difference comparisons is really useful here. And yeah, I know. Okay. So like it seems that we can. So this is a non-uniform algorithm, right? This is but intuitively it seems that we can understand such orderings. So here's a question: can we find the minimum of a plus b fast, or the median of a plus b fast in a uniform way? So this suggests that we can we understand better such orderings of some sets. Information theoretically, we have a proof here, but can we also, so this is in general a question that I think is really is suggested by this work. So another type of the same question. Let's say you have some polyhedra, which is given to you as constraint, half spaces, intersection of half spaces. So every linear function defines an ordering on the vertices of this polyhedra. And there could be only polynomially many constraints, but still an exponential number of vertices. Yes, so every linear function defines an ordering on the vertices of the polyhedra. Now, this ordering, even though it has exponentially many elements, we understand we do understand it in a uniform way also. For example, we can find the minimum element in this ordering, or the maximum element in this ordering. And what our work shows is you can actually sort, in this sense, using comparison queries, very fast also. So can we somehow, in a meaningful way, formalize a statement that we, even though there are exponentially many vertices, we can still understand such orderings that are induced by linear functions better in an algorithmic sense? So
Don't expect a positive answer.
depends on how you formalize. Look, minimum is just LP, right? When I said minimum you can find, it's just LP. To minimize a linear function over a polyhedra is just a linear program. So we can find minimum and maximum fast. I don't know.
But what about the more subsets, like a plus b plus c, it stays
Yeah.
in polylog n?
Yeah, you'll always only. It depends on how many. How many.
No, but the upper bound there.
Yeah. Because
We didn't see the proof yet, so I don't know.
I didn't say the proof yet, but it depends on the length, on the L1 norm of the vectors involved.
These sets can be much larger.
Yes. So I hope I will get to the proof. I mean, we're taking. But if not, I'll show you.
How dependent are such algorithms on how A and B, how the sum of A and B compares to? I mean,
The
A
size-
and B there may be relations. among
They're
them that-
independent. They're completely independent. Yeah. So it's true for any A and B. whether you have n squared elements there or you have just 2 n elements there. It's completely independent.
And knowing that one thing is
So
toward one end or the other.
It's a good question. I think it's a very good question, and like in a non-uniform way, if you like to do something which depends on the size of a plus b, in a uniform. Okay. There is one more example I wanted to discuss, and I will. Okay. So this last example is actually something I kind of cooked for talks. It's not in the paper, but I think it's a nice, it may yield nice puzzles. So the last example is univariate polynomials. Yeah, so here I define x to be numbers from 1 to m, integers, and f will be all polynomials of degree at most d. Okay, so here the picture, you have the numbers between 1 to m. You have 1, 2, up to m. We are given some polynomial. We have a black box access to queries about some polynomials, and we want to determine the sign for each number, whether the polynomial is positive, 0, or negative. And so, okay, when the degree of the polynomial is 1, we can just, we have an affine function, we have some linear function, and we can just use binary search to look for the sign change. There's exactly one sign change, and we need to find it. But when n equals 2, so we only need log n queries when the degree is 1. When the degree is 2, even if I give you any membership query, at the worst case, you will need n queries, right? Because I can always decide that my function is some parabola, which is just positive on one particular input, and they can make it as but the nice thing is that, and notice that here, indeed, comparison queries are not membership queries. So unlike for the linear case, here comparison queries are not membership queries, and it turns out that with comparison queries, you can do much better. So you can find it. I will not write it. You can find it using d log n squared. And comparison and label queries, you can determine the sign pattern of every degree d polynomial on 1 to m. I mean, I wrote m. Should have wrote m. And again, the information theoretic lower bound here would be d log m. So there is a quadratic gap, and also this algorithm is not uniform. I mean, here there should be a really explicit natural algorithm that tells you how to do that. Yeah, I mean, you can use it for that, right? You can, if you take two adjacent points.
The sign of the derivative.
No, comparison query is just whether the polynomial on this point is greater than or equal than the polynomial on that point, right?
No, in your model.
Yeah. Comparison query asks whether p sign of p of I minus p of j, whether p of I is greater than or equal to p of j. That's it. Okay?
I guess it wasn't your question that this gives a conditional derivative, and then you can take the degree of the polynomial to d minus 1.
Yeah.
But only buys you 1.
I mean, you will have to use somehow. By the way, if instead of the number 1 up to m, I would use the number 2 to the I, then comparison queries don't give you anything. So it's not true for any set of m numbers over the real line that you can do it in this query complexity, you need them. There should be some structure that will. What is this structure will follow from the theorem that I will hopefully prove today. So you should use it in the algorithm somehow. Okay. Okay, so these are the 3 examples, and all of them will follow as direct corollaries from one theorem whose proof is not complicated also. So, okay, do you want to make a break now?
It's up to you.
I can go on. Maybe we'll continue a little bit more and then make a break. I'm kind of skeptical, but I rather have an interaction than. Okay. So let me state maybe the main theorem. So the main theorem. So assume X is a subset of Z to the n, and that the L1 norm is at most W for every X in X. And F linear functions then can find P of F using O tilde of n log W log the size of X. Queries comparison or label. Yeah, and everything, all the 3 examples we've seen are corollary. You just need to do the. So for the polynomials, you need to linearize it. You need to consider the points in the moment curve and the.
So X is the integers?
Yes, X is a subset of the integers to the n.
Integers could be negative?
Yeah, it doesn't matter. Doesn't matter. So so I think having this geometric point of view is for us it was really useful.
Do you need really integers or just you need that the gaps between them are?
You need that when you sum X plus X, it doesn't blow up. That's what you need.
X plus X does not blow up more than a constant.
No, you need it actually. No, you can do much better than that. So you compare it with how does. So let's say X has m elements. So you compare the size of X plus X to 2 to the m, or 2 to the 2m, and you want it to be less than. It should be less. Actually, let me. No. Less than. No, I'm sorry. I was confused. You're right. Yeah. We will see it soon, and then you'll see the exact.
It should be linear, not quadratic.
Yes, I think so. But let's wait for the. But that's the point. Like qualitatively, you want X plus X to remain relatively small. Okay. So now we'll just give the key definition, and then we'll take a break, and then we'll hopefully see the proof. And the key definition I already gave on Friday, so those of you who were there, I'm sorry. Okay. Yeah, so so it turns out that really everything here boils down to a definition, and once you have this definition, the proofs are really kind of simple. So yeah, so inference, this is inference. So yeah, so let y be some subset of x, and let f be the target function. Yeah, so this is, we have query access to f. So so we say x in x, or not any x actually, x is inferred by y if sign of f of x is determined by comparison and label queries on y. Yeah, so for example, if we go to the one-dimensional case and f is an affine function, and these 2 points are y, and we know that this is plus and this is plus, and x is the point 2, so we can infer that x is also positive.
So now that you know everything, all possible label comparison queries between all pairs,
Yeah.
things and y, and that completely fixes.
Exactly, exactly. Okay, and we also, so we'll also denote infer of y f is all the things that are inferred. X in Rn, x is inferred by y. Yeah, so
Don't you want also infer y that does not depend on that?
I don't understand.
For every f, it may be a different set. Or
Right. So infer.
be large for every f or something like that.
No. It will be for a large class of f, maybe, but
For every f in your you don't know what you're talking about.
no. This is just a definition.
I understand. Yeah, but eventually you will want
I will want this.
some bound on.
Yes.
This for every f.
Yes, definitely. Now, okay, so there's only one inference rule actually that we will use. So let me just write it. Okay, so we're only dealing with linear functions. So the inference rule that we use is that, so for example, if we know that f of x1 equals 0, f of x2 equals 0, so remember that f is linear. And we know that x equals alpha x1 plus beta x2. So from this, we can infer that f of x is also 0. That's kind of trivial, right? Because it's a subspace. Another, that this is greater than 0. This is greater than 0. We know that alpha and beta are positive. Then we know that also f of x is greater than 0. That's the only thing we'll use. Okay? Let me give you an example of how we will use it. So, for example, I think this will already give.
Inferences of linear program.
Yes. So let's assume that we have, so y is like x1, x2, x3, x4, and we know that we know that
In what dimension?
doesn't matter. We know that it's just an example. F of x1 is greater than 0, and we also know that f of x4 is greater than f of x3 is greater than f of x2, which is greater than f of x1. Okay, so we sorted them, and we have this. And let's say that x equals whatever, x1 plus x4 minus x2 plus x3 minus x2. So what do I know about the label of about f of x? F is again linear.
Positive.
It's positive, right? F of x1 is, so f of x equals to f of x1 plus f of this thing plus f of that thing. And these all things are positive. So that's what we will do. That's the kind of inference we will use. We will sort things, and yeah, so more generally, if we took y, we labeled them, we know that all of them are positive, and we know that x lies in x1 plus the cone that is generated plus xi minus xj, where I is more than j, then we know that f of x is positive. And similarly for negative. So that's what we will use. That's the only thing we will use. And by the way, it's not the only inference. It's relatively weak. Okay, now let me define the inference dimension, and then we'll take a break. So the inference dimension of is the minimum k such that for every y subset of x, y at least k, there exists some x in y such that x can be inferred by y minus x and f.
I mean, you want to quantify for every x.
Thanks. Yeah, and I put the quantifier in the right place also. Okay, so let's see an example. Yeah, so what do I say? So for no matter what is the target function f, and no matter what subset y you take, as long as it has at least k elements, there is some element there. You don't know this element, but it exists. That can be removed. Then you can query all labels and all comparisons on the remaining elements, and you can infer the label of this guy also. So for example, sorry for those who are in Friday, the inference dimension of affine functions on the real line is 3. Why? Because I claim if I give you 3 elements, I take a subset y of size 3. So I claim no matter that there is always, no matter what f is, there is always one element that may depend on f that can be inferred. So there are 2 cases. If all of them positively, then I can remove this guy. The middle guy can be inferred by the 2 others. And if they are not all labeled positively, then one of the endpoints can be inferred. And the only thing I used here is that threshold functions have at most one sign change. Okay? So the inference dimension of of affine functions on the real line is 3. Okay, and the theorem we will prove after the break. Okay. So we will prove, yeah. So maybe let's take a break now, and I will fill the board with what we're going to do afterwards. Inferences are all useful for what we try to do. So the first theorem we will prove is that if this system, if x and f have inference dimension k, then we can find P of f, the partition for some unknown f in f, using order of n log n. What do I do here? K log k it should be, sorry. K log k log the size of x. Okay? Comparison and label queries. And the second theorem.
Can you say that again? Just a little harder.
Yeah, I'm sorry.
Log
K log k. K log k. And there is no n. There is a. I'm sorry. I know it's my shitty handwriting. So yeah. So and I'll show you the algorithm soon. It will clear where k log k comes from sorting something of size k.
K is the inference dimension.
K is the inference dimension.
Okay.
Log the size of x. Okay. And this is, by the way, the proof is using a fairly standard technique from generalization theory, symmetrization argument. And the second theorem will prove, which is a bit more non-deterministic. It's still, the proof is simple, but there is one non-deterministic step there, for me at least, is that showing that, you know, whenever we have this information that the L1 distance of all vectors in X that are integral vectors is small, then the inference dimension is also small. So this will be a pigeonhole argument. But
That says n log w?
n log w, yeah. Dimension log the norm bound. Yeah, n log yeah, so x, f is linear functions as usual, and x is a set of integral vectors.
I'm trying to figure out if you did this instead with x plus x.
Well, let's wait for this x plus x until it pops up in the. It's the pigeonhole argument. We'll get there. Okay, so let's begin with the first theorem. Okay, and this is the relatively standard technique in. So the way we'll prove it. So first of all, what is the algorithm? So I will present here only the randomized algorithm, but it can be de-randomized, at least in the context I've mentioned before. Okay, so we'll only see the randomized version. So the algorithm is very, very simple. At each point, we sample 2k points from X. Then we label all of these points. We check what is the label of each and every point there. And we also sort them according, you know, to the order induced by f. We have comparisons to do that, right? Then, by the way, this takes k log k queries, right? We have 4k label queries and plus sorting an array of size 4k is order of k log k queries, and this is the k log k that you see here. So we just repeat it log n times. Then we infer. This is a little bit of an abstract step. But basically, it says that for every point in X that you can infer the label, infer it. And then we just repeat until X is empty.
So the sorting, where it comes in, because the inference doesn't depend on the fact that they're ordered.
Of course it does.
Right.
Like the example I showed before, right? Before there was an example that, you know,
Yeah, but the definition.
the inference can use.
You don't have to sort. You list all the comparison answers that you might want to ask this set, and
Yeah,
from
but
these
it
you can
just,
infer.
it just says that you can bound the number of comparisons
Yes.
you're using.
Yeah,
Otherwise it would be quadratic.
Right, right,
Oh, I
right,
see.
right. And actually, it would be critical in these
You
corollaries.
can infer all the other comparison queries from these comparisons.
Exactly. You can infer n choose 2, k choose 4, k choose 2 comparison queries only k. That's the beautiful thing about sorting, right? That's that you can. There's redundancy.
So this allows you to, every time you go through, you get another set of points that you can put you know, and then you would
You remove them.
and then you just keep
Yeah, you
going.
just remove, you remove, so of course infer, and here I forgot, and remove
What about why are you removing the things in Y?
inferred
You
What
don't
is
know
Y?
the labels. What
points.
about Y?
Sorry?
Why you learn it already?
Yeah.
Why you cannot remove also?
Y is also inferred, right? Any point in Y is also inferred, because we ask label queries. Okay? So, so the claim that will finish this proof is to show that, so I want to show that it takes log n steps in expectation.
Log X.
Log x, right?
You remove a constant one.
Yeah, it will be half. On expectation, thanks. Yeah, so let's see what exactly did I write here.
Makes sense. It's not used.
Yeah, so so actually what I want to prove is something a little bit different. So let S X
One golden point.
of size 2k chosen uniformly at random. Then the expectation over S. The only randomness is in choosing this subset S of infer S, F intersection X is at least X over 2. On expectation, when you take a random S, the size of the number of points I infer from X is at least half of them. Okay?
And the two and a half are related, or can you do it with less than 2k points?
I'm sorry?
If you replace 2k by 1.5k,
So it will be
another constant there.
2/3 or whatever, or 1/3 or something like this, yeah. Well, you will see it.
Okay,
It's
so
it
it's
will,
not the 2k from before where it was
No,
important.
no, 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 no,
Okay.
no, no.
No,
No, it's a
oh,
constant
then move
bigger
the
than
case out.
that.
Okay.
Yeah.
okay. So let's prove this, and this is actually like it's a very. It's
like in the VC diagram.
it's even simpler than this.
Simpler, yeah.
So even simpler. In the VC, you take 2 samples, and then here the symmetrization trick is even simpler. Here, it's what they use in stability arguments in statistical learning, but it's very simple. Those are very like. So it's enough to show that for random x, the probability now over both S and X that X is inferred by S is at least 1/2. Right? This is just, I take this thing, it's sum of indicators. So I show that if every indicator has the expectation 1/2, so the sum of them will also have expectation X over 2. It's the
And now you look at S union X and Permutation.
perfect. Yeah. So somehow all these generalization bounds they add some redundancy to the randomness. They add an extra step, which makes life much simpler. So what we will do so instead of picking S at random and then picking X, we'll pick S union X, we'll pick a set of size 2k plus 1, and then pick X from there at random. So I repeat, instead of doing the experiment that picking S and then picking X and then checking whether X is inferred, we'll pick 2k plus 1 points and then pick one of them at random. It's an equivalent experiment. It's exactly the same distribution. But magically, this will enable us to yeah, so the point is that it suffices to prove, it's a much stronger statement, that for every S prime, let's call it, S prime of size the probability of X taken from S prime uniformly at random that X can be inferred by S prime minus X is at least 1/2. So I repeat, instead of sampling S and then sampling X, I sampled S and X, and they even take the worst case. Not even for a typical S and X. For every S union X, picking a uniform point from there will give you a probability 1/2 that it's inferred by the others. And this follows directly from the definition of inference. So why do we know? We know that this set has 2k plus 1 point. Shit. Okay, what does the definition of inference says? That as long as my set has more than k points, there is one guy there that can be inferred. This is a good guy. How many good guys do I have? Yeah, so I want to say that the probability that X is good is at least 1/2. I have a set of size 2k plus 1. I have at least k plus 1 good guys. Right? Because as long as the set is more than k, has more than k elements, I can take one guy out. So actually here it's k plus 1 over 2k plus 1.
Half the elements can be inferred from the other half.
No, half the elements are good in the sense that they can be inferred by the remaining guys. This experiment will be that, yeah, an element is good if you remove it, you query all the other elements, and then it can be inferred. But maybe also what you said is true, but you already confused me Friday, so.
You can infer in stages. I mean,
Yeah, but what does it have to?
it's a nicer statement. You have 2k element, and you erase half of them and infer them from the other half.
No, I'm not sure. I'm not sure you're right. No, I don't think, we had this discussion on Friday, and
Still not.
I'm also still confused. Yeah. No, it's not the case, because
Pick them out one by one using.
no, but you may use the comparisons on elements you remove later in the process.
You might only be able
The
to
inference
this guy by
involves
this guy,
also-
This guy has to be inferred later.
Yeah.
But if I take one off.
What does it mean that it can be inferred by the others? It means that now, this guy, you take all the others, you sort them, you find all the labels, then you can infer the label of this guy.
Okay, right.
Now, after you remove another guy. Let's call it guy number 2. Why guy number 1 can be inferred by the 2k minus 2 guys that you have now?
It's not.
It's not.
Well, it can. You first infer the one.
The label, but maybe it also depends on the ordering, on where it stays, right? The label can be inferred.
But once you have the label, you don't know the.
No, you know that you don't know where to plug it in inside the sorted array. You know that it's on the half of the plus guys or the half of the minus guys. But you.
Why is this set up? I understand that it works.
It's okay. That's the symmetry. Yeah, that's. So what I want to prove here? I want to prove that if I choose S and then I pick X uniformly at random, then with probability 1/2, X will be inferred. Now I'm saying let's consider a different experiment. We take S union X. We take 2k plus 1 points, and then we pick X uniformly at random from there. So this is another. So basically we sample a pair S and X. We can either sample it by first sampling S and then sampling X, or by sampling the union and then pick X uniformly at random. And then I say that forget the first step of sampling the union. For any union, for any 2k plus 1 points, if you take this one uniformly at random from 2k plus 1 elements, it will be inferred. probability 1/2. Okay, so that's it. And by the way, this is a standard kind of trick. It's
Where in what field?
sorry?
Standard to what?
In generalization theory, in
Statistical learning.
statistical learning.
No, it's a basic trick. It's not
Yeah, no,
like,
I was just curious, what is the?
No, I mean, somehow the nice thing there that I don't like basically how you prove generalization bounds. You look at, instead of producing the distributions like that, you first do something else and you prove a stronger statement. But the smart thing is how to add the redundancy. So you had a redundancy which is called symmetrization, right? We first sample both of them and then we forget about the first step and we just analyze the second step. So it also happens in VC bounds and somehow, so you add kind of, yeah, it's
it happens not all the employer combinatorics also.
yeah, it's double summation maybe in some sense, like.
Why can't you just pick a random k minus 1 tuple and see all the things you can infer?
Yeah, maybe this would be the double summation. Maybe, I'm not
It
sure.
will give you also a constant fraction of the points because you have about n to the k in k tuples, right? And each one gives you at least one inference.
No, but how do you know it's the right one? When you add a guy, it may not be the guy you infer. It may be the two.
No, but I'm just saying, if you look at all the k minus 1 tuples that imply something else, you have about n to the k, n choose k of those, because, and then you're averaging over n choose k minus 1 tuples. So on average, each one should infer about.
Maybe we'll see the other theorem.
Yeah, the other proof actually is more, is I said, there's a non-deterministic step. Okay, so, okay, so, so let's prove now theorem 2. So what do I need to show? I need to show that if you give me a set Y, which is sufficiently large, some n log W, then there is one guy that can be inferred. Okay, so let's fix the target function, arbitrary, and let's fix also some subset S or Y, which is sufficiently large. We will determine later what does it mean. Large. So remember now I know F, I know Y. All I need to show you is that there exists one point that can be inferred.
F is linear.
F is linear, yeah. Okay, so there is a trivial case. So case 1. There are more than, remember the dimension is n, more than n elements such that elements x, f of x equals 0. I claim that if this is the case, then one of them can be inferred. Why? If there are more than n elements, n is the dimension. If there are more than n elements in which f is 0, then there is some linear dependency there. And right, that was the first inference rule. So let's assume that this set has less than n, otherwise we are done. So the case 2, which is, so there are 3 cases, but the 2 other cases are symmetric. Case 2, there are 3. There are many x's such that f of x is greater than 0. Yeah, so if we have less than n here, then half will be positive, half of the remaining will be positive and negative, just like the majority. Just like so let's call these guys x1 up to xm. So we know that all the labels are positive.
Wait, sorry, what did you say before? There's at least n over 2 of them?
No,
There's-
and
Yeah, so the first case, when there are n elements in
Okay, so
In
the
Y.
majority of the stuff
In
in
Y.
Y.
that's only in everything is in y, yeah.
So you mean the majority of things in Y
Yeah.
are positive? Yeah, gotcha.
Yeah, so let's say the majority of things in y are positive, so at least y over 3 guys are positive.
Yep.
Okay, let's call them x1 up to xm, and let's further assume that after comparing, we know that f of x1 is lesser than or equal to f of x2 up to f of xm. And this is, of course, by assumption greater than 0. Okay, so this we all know. What I want to show is that there is some guy here, somewhere in the middle, xi, that can be inferred by the others. Okay? Now I'm doing it right. Okay, so, and we're going to use the inference rules that I mentioned before. If we know that two things are positive and another thing is a non-negative combination of them, then it must be also positive. So here is the non-deterministic step. Anyone has suggestions for how to do it? I want to show that if m is sufficiently large, then we can find such a guy.
You want to find a linear combination. and
Right.
you're going to use the fact that the numbers
What kind of
are
linear combinations do you want to use?
non-negative.
Yeah, but even more? Boolean combination, that's the point. The point is, so okay, what we'll show, so I claim that it is enough to show.
Boolean will be not plus
Wait, wait.
minus 1.
Yeah, wait 1 second, enough to show
Subtract two that are equal.
there exists beta prime, beta in 0, 1 to the m.
So the difference will be plus minus 1.
Yes, you're right. Such that sum this is for me the non-deterministic step in the proof. I claim that it's enough to find two distinct Boolean combinations that give you the same vector. Okay? And why is it enough? Okay, so this I will leave it to you, but basically you look at the largest coefficient which is different. You want to do it? So you look at the largest coefficient which is different. So if I star is the max I such that beta prime I, then can write xi star minus xi as a minus x1 as a non-negative combination of xi minus xj, where I is more than j. Yeah, and this is just
This is xi star minus x1.
minus x1, yes. So you add you add the whom is it? Two. Yeah. Yeah. So this is really a trivial statement, but I can prove it. But the point is that now you basically you look at this maximum element for which beta I is different than beta I star. You move it to one side, you move all the rest to the other side, and then you add. So you have like xi plus 1 minus xi equals something here, and then you add plus xi minus x1 here, and this will cancel. Yeah?
You
Believe-
can do it if anybody wants. You have plenty of time.
I do?
Doesn't matter.
I have 10 minutes.
Why
It's until 12:30.
Yeah.
Okay, so you want to do it?
Then video can be here.
Okay, so what do we know? We know that xi plus 1, xi star plus 1 minus xi star equals some I less than I star of alpha I xi plus 1 minus xi. Now, what do we know about the alpha i's? The alpha i's are at least minus 1. Yeah, what I did is I took this, I subtracted them. Yeah, I took the maximal guy onto that side, and I removed all the others to the other side. And all the coefficients were zeros and ones, so after subtracting, it may become minus 1. Okay? And now what do? I just add xi minus, I subtract minus xi. So, yeah, minus xi minus x1. Or plus xi minus x1. I add to both sides. Yeah, so I just want to get xi star, sorry, thanks.
So why is alpha I greater than 1?
Because what are the alpha i's? Are just beta I prime minus beta double prime minus beta prime. And the betas are zeros and ones. Alpha is the difference of two betas. Right? We began with the fact that we have two Boolean linear combinations.
Divide by, so I is
So I multiply.
difference. You need to divide by beta I prime minus beta I double prime?
No, we know that beta I star prime minus beta I star double prime is 1. Because these are Boolean combinations, these are 0, 1 numbers,
Okay.
and they are different.
Okay, forgot that they're good.
So we just can multiply by minus 1 and have it. Okay. So now I want basically to make all these alpha i's. So they are minus 1. I need a non-negative combination, so I add this thing. What is xi star? So here on the right-hand side, on the left-hand side, I got xi plus 1 minus x1. And here what happens? What is xi star minus x1? Yeah, so xi star minus x1, we can write it as xi star plus xi. Okay, now I'm confused. Yeah, it's exactly, that's what I didn't want to do it on board, but we just write xi star minus x1 as a sum of, that was the one I was doing, telescopic sum, and this affects by adding at least 1 to each alpha I. This is the effect. Oui.
So now you're concluding,
So yeah, so now I get here that now I conclude this thing, that xi star minus x1 is a non-negative combination of xi minus xj, where I is more than j. And what does this give us? That xi star is equals to x1 plus sum of xi minus xj, where I is greater than j. So when you take f of it, it's at least f of x1 plus the sum of the f's, and this is all positive.
So does it mean that this is not in y?
So no, so what I showed is that there exists some xi star in y. The whole point was to show that there is some element in y whose label can be inferred. So we took all of them, we sorted. And yeah, assuming that, I still owe you this thing.
Is this in y?
Yeah, all of them, the x1, x2 up to xm are all in y.
The difference should be in y?
The difference is not in y, but it's a comparison query on y. We have the,
Oh, okay, okay.
it's a comparison query. Okay, so that's how we use the comparison queries. Okay, so basically the whole idea of that was to show you that it suffices to show that there are two distinct Boolean combinations that are equal of these differences, these consecutive differences that are equal. And then we get to the previous inference rule that, you know, we have a. Now, how do we show this thing? And here comes the pigeonhole argument. Yeah, so let's show that. So how many Boolean combinations like that do we have? 2 to the m, right? We have 2 to the m Boolean combinations. Okay, on the other hand, how many vectors? And so these are all integral vectors. How many of these do we have?
W to the m to the n.
So it's like it's okay. It's like choosing
W to the n.
W to the up.
roughly. No, it should be W to the n. Yeah,
Yeah.
yeah. N is constant. N is the dimension. We think of it as a constant. M we can, you know, we can increase m. We want to show that m, when m is sufficiently large, we'll have two things that are equal. And yeah, so that's it. And now there's just calculation to, you know, to.
And this is what would be an NP-hard problem in general to make this non-explicit, non-uniform algorithm into one. That
Yeah, even
the
subsets.
inference step may in some cases be a very hard problem.
Yes. Yeah, so basically the inference step is you need to go over all points in X and to ask whether it's inferred. And inferred, as we, at least this kind of inference is just solving some linear program feasibility problem. Which is still, you can do it polynomial time, but the problem for subset sum, for instance, so if you want to use it for subset sum, you have to, at each inference step, to go through 2 to the n elements and check if they're inferred. Right, so I erased the algorithm. Okay, let me now conclude with some open questions. How much time do I have?
You have
Good, 12:13. Okay, so
Just thinking, why is it W to the n?
Yeah, I just.
I thought it was obvious.
you said it. Okay, so let's do the. I just believed you actually. I didn't.
Each one has a value up to W.
So you have what do you want to count? What is the norm of xi minus xi of this kind of vector?
When you say this, you mean the sum or
The sum, everything here. The norm is at most twice the norm of what we began with, L1 norm. Right, we assume that the xi's have L1 norm at most W. All of them. And now we take some, not twice, yeah, so it's at most m times the, right? And then now you ask yourself how many vectors of L1 norm, given L1 norm, integral vectors do we have? And this is, you know.
There should be some m there.
Yeah, so yeah, there's in the
Yeah, let me just write.
M W to the n.
Thanks. Yeah, the point is that it's much slower than the other term. Okay, so now open questions. So
You have to specify the inference dimension, the n log W.
I don't know. Let me think 1 second. Maybe, I mean, I did think about it, but so in some cases it was typed, but it was more in the previous paper that I need to think about it. I can't just. But you know, it cannot be much smaller because you basically get the information theoretic lower bound for, so maybe you can save a log factor at most. Okay, so let's discuss some open problems.
That's probably better to write with white or the
Okay. Set up. So, so open. So the first open problem is in non-uniform complexity still, non-uniform. Is, you know, what is, let's assume now we still, f is the set of linear functions, but x now is an arbitrary subset of Rn. And we can use membership queries. So this is the problem that was studied since the 80s. And yeah, so basically you have, you know, you have some linear decision tree, yeah. So you get some arbitrary points, set x of size, you know, k, m, and you want to find all labels according to some unknown linear function using as few membership queries as possible. Now, so the best, so yeah, this is arbitrary x, linear membership queries. So the best known upper bound is so in Rn. Actually, let's call it Rd now. It will be so x is a subset of Rd. The best known upper bound is d square log n, roughly d square log n, and the lower bound n is the size n is the size of x. So d square log n is the best known upper bound. Bound is d log n. What is the truth? And I think actually you can think of it as a geometric variant of the partition number versus you know, communication complexity of protocols. What do I mean by that? Let me try and tell you my intuition. So what is the so what in communication complexity? We know that any partition of the input space to rectangle can be refined by a protocol partition whose depth is at most quadratic. So I repeat, any partition to rectangles, yeah, so we have some partition of the input space to rectangles. So there is a protocol partition. What is the protocol partition? Protocol partition, in each step, it has some hierarchy, and in each step, you either take a line like that or a line like that. So maybe like this. Okay? Now, this question, you can think of it as follows. You are given, so here it's convenient to think about the dual problem, but now assume that you are given some partition of Rn, not by horizontal and vertical lines, but by arbitrary lines. This is basically what x gives you. So here there is one region of W's, here there's another region of W's. So you are given some partition by hyperplane arrangement of Rd. And what is a linear decision tree? What is our algorithm? It's exactly protocol partitions. In each step, you can take a linear function, and you know, either it's plus, minus, or 0, and then you recurse. So it's exactly, so it's exactly the geometric variant of protocol number versus partition number. And the nice thing is that we also have the same kind of gaps, right? So if you take n to be d square, so you know, so d log n is, so the lower bound is d log n. D log n is just d log d. And the upper bound is d square log n. this square log d, roughly. So we exactly have this quadratic gap. And I don't know if it's coincidence or maybe there is some deeper relationship here between this geometric variant of
It seems like you should take the generic hyperplanar and apply them to the question.
for a lower bound, like to improve the lower bound.
Yeah, for knowing the right answer.
What do you mean by generic?
Like when x is in general position,
Yeah,
maybe. Okay, so this is one.
So the upper bound is like similar to the
No, it's very geometric. It's very, very geometric. It's actually a recent paper from Ezra and Sharir.
Polynomial upper bound was known.
Yes. No, but I think like this, yeah, polynomial upper bound you can get. That's there is a paper by from '84, right? Yeah. Okay, so this is one question. Another question that we actually discussed with Mark on Friday is that, here we use a gadget which is comparison query, so it's a kind of a simple type of membership query that you can also use. It's not all membership queries, but can we, and one thing I didn't show today is that with comparison queries already on the plane, you can do everything in logarithmic time. But in the 3 dimension, there is a lot, again, there are hard point sets. So are there other gadgets, maybe 3-wise comparisons, or what Mark suggested of taking the vector product, or something like that, that will work in general, and I think that's, this can also actually maybe solve this problem, if it works.
So what is the question? Having a new type?
Yeah, so we have, maybe. So what is a comparison query? A comparison query is just it's a mapping from RD to the 2 to RD. Yeah, so xy goes to x minus y. And then you apply membership query on this thing. And Mark suggested that, if you want like to take maybe d minus 1 vectors, you can take their product. So you look at the hyperplane they span, and then you take a normal to the hyperplane, you apply membership queries on this thing. You can apply the same analysis, the same inference dimension analysis will work. All you need to show is that the inference dimension of an arbitrary point set is small with respect to whatever gadget you have in mind. And maybe this can actually solve this general problem in the if the upper bound can be improved. Okay. And another cute puzzle, I think, is just to understand. Now we have a polynomials over the line, over the numbers 1 to m. How many comparison label queries do we need to find their signs? Okay, now in uniform complexity. So one obvious question is to use like the previous works did. They first gave a linear decision tree, and then they designed a uniform algorithm. So to do the same thing with with these kind of techniques, and I heard that actually it's being done by.
What do you mean? So there'll be uniform algorithm?
Like to shave another log factor from 3 sum. Now the best upper bound is n squared over some log n over log n or something like this. Maybe shave another log factor from it using and another one last question I want to mention has to do with a work of Carmosino, Gao, Impagliazzo, Mihajlin, Paturi, and Schneider, which is the non-deterministic fine-grained complexity. So let's consider the problem of 3 sum. So we're given an array. We want to check if there are 3 numbers that sum to 0. It's very easy to prove that an array is a yes instance of 3 sum. I just exhibit the 3 numbers, but can we prove fast in the polynomial sense fast that an array is not a yes instance of 3 sum? I want to prove somehow that no triplet sums to 0. So these guys, they gave an algorithm of n to the 1.5. So instead of n squared, n square root of n to do it. But it uses very different, it uses like finite field theory, like prime numbers, and it's very different than the geometric methods here. But here also, like essentially for 3-sum, we have a decision tree of n log n. So you have a proof, a very short proof of size only n log n, that there is no triplet that comes to 0, but we cannot verify it fast.
Are there lower bounds?
I don't know. I don't know.
This can be potentially linear. So all you want is just a non-deterministic algorithm. It's not restricted. You can do whatever you want today.
Yes.
You know how the upper bound works.
So this is a refutation question, right? Like
Yeah.
you want to refute.
Yeah.
And so sorry, just to understand, you want an efficient algorithm for refutation?
Non-deterministic. Yeah, efficient here means
Huh?
It's just like the size of it.
Just the size of it.
yeah, efficient means in this fine-grained sense. Yeah. So. So I just want to say that we can build these linear decision trees, and then you can follow the path. You take a no instance, you get a bunch of you get the computation path, all the sign queries that were made. So this is a very short proof, and this already has information theoretically. It's a proof. There is enough information there to prove that. But the bottleneck is to indeed verify this proof. So we have very short proofs, but the verification time is long. But yeah, I think it's a nice question. Yeah, and the last question was about sorting, but I already asked it in the middle. Yeah, so in what sense can we sort? So this gives you very, very fast sorting algorithm for A plus B for any, as I said, linear function over vertices of a polytope. Information theoretically, we understand such ordering very well. Can we formalize it algorithmically?
So finding the median of.
I think this is hard actually, but
Well,
even over the
I said
Boolean
it's
Q.
hard, you argue.
No, I said okay, I didn't understand what you meant. But yes, yeah.
You don't expect it to be.
Median, no, but I do believe, look, finding the minimum is easy,
Yeah.
and it's not trivial. Like it's LP, right? It's ellipsoid. So is there any meaningful extension of this? Like, I don't know, you can sort it very fast, information theoretically. I mean, there should be,
You can sort it, you can find the median.
non-uniform way, yeah.
So it's exact.
Yeah.
I just wanted to ask you, so the algorithm is always like oblivious, the decision tree. It just, picks instead of random.
The randomized algorithm is oblivious. Once you de-randomize
Not
it,
quite
so
oblivious. It
basically, like,
removes
fix-
element. It removes
Yeah,
element.
and
So
then it
it
decides
then
everything
it's
about this, so it doesn't like make decisions on, and even not
Right, makes
randomization.
decision. The sample, the next sample depends on those you throw away. It is. It's not.
You mean for
oblivious.
the deterministic version of it?
No, it's not probabilistic. You remove some subset and then you sample from the remaining ones. It's important to
Okay,
remain.
you're right, never mind.
yeah, it's oblivious in the sense that it's every step you repeat the same thing. You don't need any memory.
No.
And,
But you do. You need to
yeah.
know which.
It depends.
When you X, this is
Yeah.
Exactly.
definitely adapted.
Yes,
Yeah,
yes,
and
yes,
you have to, I guess you do have to do that, you can't.
yes. Yeah.
No, maybe you don't have
Yeah, maybe
to
you
do
don't,
that.
yeah.
Maybe you don't
I
have to
don't
do
see
that.
that.
You don't have to do it.
Maybe you can resample and maybe your hope is to kill another half or sort of. Maybe
But you allow it to depend on the initial x, but otherwise oblivious. That's what you mean.
Yeah.
And you
I
might
mean,
have to
it's
take
not.
more
It's
samples.
possible that you
It is
take more.
possible.
Yeah. It's possible that it can be made oblivious.
The only other thing I wanted to ask you is, so like all of this hinges on this, total search problem that we finally get to, that's like weak pigeonhole, or like pigeonhole. But you can like think about whether that could be solved, how efficiently it can be solved as you run over your example problems. Obviously some of them is gonna be impossible, but others maybe not, and then that'll give you a real algorithm.
Yes,
Have you thought
yes.
about that, or like
Yeah, so
like the polynomial approach?
yeah, I didn't spend so much time on that, but I think it's at least a nice puzzle. I don't know if it's, like univariate polynomial of degree up to d over 1 to m.
But I mean, in your framework, like instead of just,
Yeah, in the framework. So you just
so
so-
have to show how to solve this total search problem.
Yeah, that's an yeah. Like to, okay, I see what you're saying. Yeah, that's also. Yeah, I thought like a very explicit the algorithm that is really, but like
stick with your framework and just see if this particular search.
to see if this can be implemented efficiently for this particular case. Yes. Yeah, by the way, for the polynomials, you can even, so our result gives you also that you can, so again, you have the number 1 to m, you have an unknown polynomial of degree at most d. It defines an ordering on these numbers. I is less than j, if p of I less than p of j. You can sort information theoretically, you can sort these n numbers using d square log square n, using this theorem. You can sort it, but you will have to use these difference comparison queries. Can we, so maybe such orderings you can understand well. Can you find the median? You have a polynomial of degree at most d, numbers 1 up to m. Can you find the median with respect to this ordering in sublinear time? I think, yeah, so. Yes?
Somewhat, it's not exactly well formulated, I'm sure. What if the set X is itself, rather than thinking of it sort of as vectors, it can be thought of as matrices of some shape. So it's not D, but it's K times L, some sort of shape.
You put like the rows of a matrix.
Yeah, and F is linear on its rows or something. I mean, are there questions that you can do these techniques can they be applied to sort of I don't know, distinguishers in terms of the rank of such objects? I mean, it seems like a much more complicated kind of deciding whether you can say I have no idea because it seems like it could be a complete
So
idea.
I do know an example of in 3 dimensions in which the matrix you described will presumably have rank 3, and then you cannot do anything for linear functions and comparison using just comparison queries. So there is a point set in R3 with huge coefficients, of course, for which you cannot do anything using comparison queries. That's why I asked the question that Mark, that I discussed with Mark. Can you find another gadget, not comparisons, like 3-dimensional gadget, that will extend to higher?
I think the question was different.
Okay, maybe.
For you, maybe the linear functions are like inner products with rank 1 function.
So quadratic forms.
But I don't know. I guess one can ask several questions about matrices.
So the question is that X now is a set of matrices rather than a set of vectors, and you want some.
And you don't look at all linear functions.
Right.
I see. Yeah. So certainly this connection between inference dimension and the algorithm is completely abstract. The only thing where we use the linear functions in the RD was in this pigeonhole argument. All the rest is completely abstract. So